My name is Daniel Stein, and this is Lab 3 RC circuits. The aim of Lab 3 was to verify circuit laws to measure currents and voltage drops in series/parallel configurations. We observed the RC charging-discharging behavior. The models and principles was Ohm's law, Kirchhoff's law, charge conservation, ideal meter models, RC model. Our system consists of the circuit components, batteries, resistors, meters, and capacitors. The surrounding include the connecting wires and the environment, which contribute to non-ideal behavior. Series currents were consistent, averaging approximately 18 milliamps. Measured resistor values showed an 8 to 10% deviation from nominal. The RC behavior exhibited a time constant that was much longer in practice than predicted by ideal component values. Some assumptions that we had to make was the ideal capacitor was with capacitance C, resistance R is constant. The battery is also modeled as an ideal voltage source plus an internal resistance R battery. R is constant. Wires have negligible resistance. Capacitor is ideal with capacitance C. The total series resistance R is constant. These are some of the equations we had to use, and through these equations we determined that charging follows an exponential rise, discharging follows an exponential decay. This is the data and measurements that we took. As you can see here, we have the components and what we derived, and this is the nominal. And these are all our measurements that we took and our calculations. So if you read all these, I'll just kind of sum up everything. Our measured currents 17 to 19 milliamp range during charging and discharging. Voltage drops were 0.8 volts and 1.7 volts. Those were the 47 ohm bulb and 100 ohm bulb. Resistances right here, charging and discharging times, RC constants, Kirchhoff loop check, and what we concluded was the data confirms exponential charging and discharging behavior, validates Kirchhoff and Ohm's law with measurement uncertainty. So we compare the data and the model. And these are our measured data, and we determined our model predictions, which were T-series currents equal, measured I1 and I2 agree within a few percent, and that we determined Kirchhoff's loop, the sum of drops should equal the battery voltage. So here are some figures and diagrams. As you can see here, this is charge and voltage compared, and you can see as the charge or the capacitor increases in voltage, this is the charging and then this is discharging. And basically as voltage or as time increases, voltage comes to a constant time because that's just how the capacitor it just works. The voltage increases until it reaches this, and then the current drops to 0. That's what these graphs are showing. So these are our apparatus and demo. We use 1.5 volt cells and 47 ohm and 100 ohm resistors and a voltmeter. This is charging and discharging of the capacitor, and here is the parallel capacitor and series circuit. Some errors that we experienced was internal resistance of the battery. The battery was already partially depleted. Measured R values differed from the nominal by 8 to 10%. Voltmeter high R reduces circuit current. Timing for RC measurements were imperfect, and connection quality between wires, resistance and wires, it wasn't the best. Discussion. The data validates Ohm's law and Kirchhoff's rules in direction and magnitude. What if no resistor was with the capacitor? The ideal model predicts instantaneous charging and infinite initial current. This is unreasonable because real circuits will always have R totals greater than 0. Observed RC times reflects different R totals and different loads in the trials. Voltmeter high resistance preserves voltage reading, but it suppresses the current. Ammeter with low resistance measured current, but induces a small voltage drop that needs to be placed in series. In conclusion, the experimental results math, the qualitative predictions from Ohm's law and Kirchhoff's law, and are consistent when measured, are unincluded. The differences from idea expectations are explained by battery, internal resistance, resistors, and meter loading. Time-dependent charging was observed and confirmed the exponential nature of V and I in RC current, showing exponential decay. In conclusion, the experimental data supports the theoretical RC model.